Bismillahirrahmanirrahim, and welcome to the new lecture on graph theory. So current topic is basically the minimum spanning tree. So that is MST, minimum spanning tree. A minimum spanning tree is basically a spanning tree with a minimum sum of edge weights. So that means that if you calculate a spanning tree and you sum all the edge weights, then it should be the minimum for over all the spanning trees that you can generate from that graph. Let's say you have a graph with three vertices, and the costs are 3, 7 and 5. You can see the edge weight of AB is 3, AC is 7 and BC is 5. We can generate different spanning trees from this. So like this one, we can generate this one, and we can generate this one. So these are the all possible spanning trees. So the cost of this spanning tree is 10, the cost of this one is 8, and the cost of this one is 12. So here we can say that the minimum cost is 8. So it means, so this is our minimum spanning tree. Let's say we have another graph with 4 vertices and 4 edges. So we can have different spanning trees from this graph, just like this one, this one, this one, and this one. Let's say the cost of these edges are 3, 7, 2, 5. Then the cost of this spanning tree is 2 plus 5, 7, and plus 7, 14. 3 plus 7, then 5, 15. So 2 plus 3, 5 plus 7 is 12, and this is okay. So these are two the same ones. So this should be like this one. So this is not there. So this is 3 plus 7 plus 5, 10 plus 5. So it is the same this one. So not this one, but this should be included. Okay, so this is 3 plus 2 plus 5, this is 10. So this is, so if I draw it neatly, so it should be like this one. So this is tree. So this is our going to be the spanning tree with a minimum total over all edge weights. There are lots of applications of MST. So for example, finding the least expensive way to connect to the set of cities. So you will be connecting the cities with a minimum distance or with a minimum cost expenses, or connecting the terminals with the minimum expenses and connecting the computers with the minimum expenses. So these are the different applications of MSTs. And question rises whether a spanning tree is a unique one, or can be more than one spanning trees in the same graph. Yes, it is very much possible that you may encounter more than one spanning trees, but the cost of all those trees would be the same. For example, in this example, you can say, and this is a spanning trees, and that is highlighted here. So this is a spanning tree dropping this edge, and in this sorry, so this is the spanning tree dropping this edge, so the cost would be 3. So in the other one, this is going to be another spanning tree, and the cost would be same 3. So this graph is having two spanning trees with the cost 3. And as we know that this is a spanning tree, So the number of edges in this spanning tree would always be v minus 1 because it should be connected and it is a tree. The generic algorithm of MST is you create a set A of edges. So this set will be having the edges that belongs to MST at the end of this algorithm, and then it will initially it will be empty. Then after that your incremented edges, you will add edges into this set A such that the every edge that you add in this one should be the safe edge. So next I will be discussing what is the safe edge. A formal definition of safe edge is that an edge UV is said to be the safe edge for A if and only if A union U comma V is a subset of some MST. So that means if you add this edge into the MST, that is A, then it would be belonging to some MST. So then only then we will be saying that this edge UV is a safe edge. So here we can see that this is a generic algorithm for that we have been discussing, starting with the empty spanning tree, while A is not a spanning tree, until the completion of the A to be a complete tree covering all the vertices. Find a safe edge UV. We need to find a safe edge for this spanning tree, and if it is the safe edge, then we will add this edge into this set A, and finally at the termination of this loop we will return an spanning tree that is named A. The main question in this algorithm is how to find this safe edge. Okay, so suppose we have this example in which there are 6 vertices, multiple edges, every edge has some cost. So let's say we have 2 sets, S and V minus S. So total edges, total vertices are V. So there is one edge that is S, so the remaining is V minus S, and we know that this S is subset of V. Okay, so to calculate an MST, there should be one edge that is connecting S with V minus S. So we can see in this component that is S, and in this component that is V minus S, there are 2 edges crossing this one. So there are 2 and 4. So to connect these 2 components, we need to choose one of these edges. So some edge should be selected that is connecting S and V minus S. So what would be the best option? So we have 2 options right now, that is this edge AD having the cost 2 and this edge CF having the cost 4. So the question is, why not least weight edge? So if we have the option, we can select this one and then select this one. So it would be better if we select this one because we need to find the minimum spanning tree. So our spanning tree with a minimum cost, so we should be selecting an edge that is with a minimum cost, and that is actually the answer of the safe edge. How to find a safe edge? Continuing the same thing, we can say that we can distinguish between these 2 sets S and V minus S with a cut, and suppose this is the cut, so let's call it cut. So this cut is going to make divide this graph into 2 parts. One is S and one is V minus S, and obviously these 2 sets S and V minus S are disjoint sets. From here we can see that this cut, this red cut, crosses respects A. So what does it mean that by respecting? So that means this cut is not crossing any edge in the A, or the vice versa is also possible. So from here we can see that the light edge or the lightweight edge would be an edge that is minimum over all edges crossing this cut. So this cut is being crossed by two edges, that is AD and CF. So the light edge would be 2. So because its cost is, or its weight is the lightest over all the edges that are crossing this cut. And if this edge, this light edge basically is called the safe edge that we have discussed previously here also. So so we can say that the lightweight cut that crossing the lightweight edge that crossing the cut is actually the safe edge. Okay, coming towards the algorithm. So there are basically two algorithms that in this course, that one is Prim's algorithm and the other one is Kruskal algorithm. So starting with the first one, that is Prim's algorithm. Okay, I stopping this video here right here, and we'll continue the next video with the Prim's algorithm, so that we can keep these algorithms separately in separate videos. So this was the basic concept of Prim's algorithm and how different researchers have generated their one on the basis of the generic MST algorithm. So in the next video I will be discussing the Prim's algorithm.